Okay, so um, I mentioned last time that basically the way that we're going to progress through this book is we'll start with compass and straight edge constructions. This leads directly to axiomatic treatment of Euclidean geometry. So we will talk about both the axioms or postulates that Euclid directly stated, and then we'll also mention the holes that were, or the gaps that were later filled in by all of this, by later mathematicians in the it was eventually the end of the 1800s, into the 19th century is when a lot of the like final gaps were filled in, but we'll talk about the development, from literally from Euclid, from the elements, so from about 2,300 years ago. Okay, so compass and straight edge constructions. What's the idea? The idea is that for the ancient Greeks, geometry arose out of the things that could be constructed with these basic things, or these basic tools. And I'll list here in a second after I've demonstrated. Look, there's straight edge. As I mentioned last time, this straight edge, has markings on it. It is a ruler, but our straight edge is going to be an idealized straight edge that doesn't actually have any markings on it, so you can just ignore any of the markings that show up. And compass, okay. So here are our two tools. So where do these come from in my axiomatic treatment? Well, there's a couple of, so first, assumptions. So what are the things that we're allowed to do, first of all? So first thing is, or maybe I should even ask that question. So what things am I allowed to do? Okay. So I can draw a straight line segment between any 2 points. Okay. So given any 2 points, I can draw a straight line segment between them. And I can also extend a straight line segment indefinitely. Okay, so even though we consider a line technically to be this thing with infinite length, the Greeks typically wanted to avoid any kind of dealing with infinity, and so line segments were almost exclusively the things that they dealt with. But in order to deal with some of these diagrams that are going to arise and the things that you want to prove, the line segment itself is not going to be enough. You need to extend that line segment, and that's why number 2 is needed. And so these two things together tell me that I have a straight edge. Okay. Okay, that's what these two things are telling me. All right, so what am I allowed to do? I have 2 points. I am allowed to draw line segment between those 2 points. There it is. Okay, so this is line segment AB. Okay, some notation first. So we will call this line segment AB. If we are talking about the length of this line segment, we would use this notation. So absolute value bars around the line segment AB. Okay. Okay. Now, it may be tempting to say, well, if I want to compute the length of AB, then I just actually measure it like this. Looks like I've drawn an exactly like 1-inch thing or something, right? But actually, it turns out that, can't do this because I didn't say anything about distance here. I didn't say anything about length in these first two. Okay, so my straight edge is only used for these two things. Okay. All right, so then what's the next thing that I can do? So next thing I'm allowed to do is draw a circle with given center and radius. Okay. This says that I have a compass. Okay, so this is where my compass comes in. This is also where the notion of measuring comes in, so I'll talk about that in a second. I can draw a circle with given center and radius, so my center I'll call the point C, and the radius is whatever distance I open my compass to. So there, we'll say that here's my compass, or here's my radius, and so the circle I draw looks like this. Okay. All right. Okay. Now, encoded in that, of course, we're taking for granted what is the definition of a circle. So then a circle is just the collection or the set of points that are some fixed distance from some other specified point called the center, right? And so in this case, this fixed distance is whatever distance I've opened my compass to. So that, the distance between the points there, is the radius of my circle, and of course the whole point of that motion that I did was to trace out those points that are that distance from C. Okay. All right. But again, this is really telling you that the distance between C and any point on this circle is exactly this distance you've opened your compass to. Alternatively, if I fix my compass on one of these points, A, B, and then arrange so that now I have my compass open exactly that amount, this is why the compass is a measuring tool in this sense. In compass and straight edge constructions, the straight edge is not a ruler, it's the compass that's the ruler. It's the compass that's the measuring tool. And the way that it measures is it stores this length of the line segment AB. Okay, so it stores AB here, and I can store this length and then transfer it elsewhere in my diagram. Okay, now of course, the transferring it elsewhere, how's that going to happen? Well, the way that this typically takes place is me drawing circles of different radii, in my diagram and making markings with considering the intersections of those circles with other line segments in the diagram. But this is how measuring is done in my compass and straight edge construction. So no ruler, just compass is the only tool I have to deal with that. Okay, and so how does this what does this lead to? So we're going to see that geometrically we can actually construct all sorts of things that you might have thought about only algebraically. So it turns out these tools alone will allow us to construct many objects that on the surface don't have anything to do with geometry. So one example of this is I can come up with a notion of adding and subtracting using this, right? So I can come up with addition and subtraction. Okay. All right. So what does addition and subtraction look like? So let's say that I have some, say I have a line segment CD. So let's just take CD here. So here's C, here's D. Okay, and I'm considering the line segment between these things. Okay. And let's say that I want to add the line segment AB from earlier to this. So what if I want to add the length of the line segment AB from earlier to the length of the line segment CD? How does this work? What about subtraction? Well, I still have my compass open to this same length, so let's look on this other sheet. I have my compass set to this length AB. So now it is stored, okay, in my compass. And so then I take this thing and I pick one of the points. I'm going to pick D here. And after I've chosen D, I draw the circle of that radius centered at D. Okay. All right. So, what do I do now? Well, I am allowed to, so this, if I just pick any point here, right, from D onto this circle, and I make line segment, this line segment, I've gone a little bit over the circle there, but that's okay. This line segment here, what is its length? Well, the length of this line segment is the length of AB, right? And of course that would be true because I've fixed that radius in my compass here. That would be true for the line segment from D to any point on this circle. Okay, furthermore, here I'm looking for a point that is on my circle that is directly on the other side of D from C. But what am I really doing there? Right, what I'm really doing is I'm asking for, the point that is collinear with both C and D, right? The point that lies on this same line. But rather than try to eyeball one of these and pick it out and then extend it, I can actually just extend this line segment I started with, right? That was one of my assumptions, is that I can extend a line segment indefinitely. Oh, went past the ruler there, so ignore this bit. That's bad. We don't like that. Okay. So I've extended my line segment since I'm allowed to do that, and I get some other point here, okay, on my line. What's significant about that? Well, the idea now is that this line segment, considered from C to whatever I'm calling this point, we'll say E, if I want to call it that. This line segment from C to E, right, that has length what? Well, it's the length of CD, whatever that was, and then tacked on is this length of the line segment AB. So what this really is the length of CD plus the length of AB. Okay. And so in that way, we've geometrically constructed addition from compass and straight edge only, right? This is what we've done. Okay. But in this same diagram, we've constructed subtraction. So where is that? Well, this radius of the circle is my length AB, or my length of the line segment AB. Here's the length of CD. So then where is CD minus AB? Well, it's here. All right, what do I mean by it's here? This little piece, right, is the length of the line segment CD minus the length of the line segment AB. Okay. In the same way. Okay. So in this way, we've constructed addition and subtraction of lengths, okay, using compass and straightedge. Now, you may be asking yourself one thing. Since last time, when you asked, like, do I need a compass for this? Having a straight edge is no problem. You have something like that lying around, right? Even if you have to use, like, the edge of a book or something. But the compass you might not have laying around. You don't need this. So the only thing is it can help intuitively to have one that you're actually turning around when you're looking at these diagrams or trying to come up with these constructions. It can definitely help, but it's not necessary as long as you keep in mind, right, if you use your imagination and keep in mind what it is this thing is allowed to do. In order to actually mimic this on a diagram, rather than drawing full circles, you could make sketches. It's okay if they're not 100% accurate. Of course, the diagram being accurate, this being an actual circle that you've traced out with a compass, makes the thing easier to look at. But in terms of these compass and straight edge constructions, you can mimic the effect of a compass just with markings. Okay, and if you're careful about what's going on and what you're allowed to do with a compass, then that's perfectly fine. Okay. All right. So this is one construction. The very first construction that Euclid does in the elements. By the way, that gives me by the end of class, I'm gonna type up a URL. Maybe I'll add it to Elms that actually gives you a nice. It is Euclid's Elements online for free. You can have a look at that I think is pretty good translation. I think it even has like clickable diagrams you can move around. So I'll do that by the end of lecture. If I don't get it by the end of lecture, I'll post it to Elms over the weekend. Okay. So then the very first the very first construction that Euclid does is the construction of the equilateral triangle. Okay. So Euclid's construction of an equilateral triangle with a given edge. Okay. All right. So let's say that we are given an edge for this equilateral triangle. So the given edge we'll call AB. There it is. Okay, so there's our edge. So I want to construct, using compass and straight edge only, an equilateral triangle that has this line segment AB as one of its sides. Okay, so how do I do this? Okay, so there's 3 steps. So first step, so I fix a radius using my compass. I fix this radius AB. Okay, so there we go. All right. And once I've done that, I draw the circle of radius AB with center A. So draw the circle of radius AB and center A. Secondly, I'm going to draw the circle of radius AB with center B. So to see how this works, I have my first circle, and I've moved here. I'm not going to draw the entire circle, but I could if I wanted to. So this is my part of the circle of radius AB with center A. Now I do the same thing from B. Okay. What is it that I'm looking for here? I choose one of these intersection points of these circles. Okay, so I choose one of these things. I can choose this one or I can choose this one. It's not going to ultimately matter, and you can test that logic after I've written this out, and I'll call this C. And then I draw the line segment from A to C and from B to C. And this is an equilateral triangle. Okay. Why is it an equilateral triangle? Okay, well, we have to just check. So the length of this, obviously, is AB. What is the length of the line segment BC? Well, the length of the line segment BC is the same as the length of the line segment AB. Okay. Now, in the diagram, we can see this with the compass. Right? Similarly, the length of AC and AB are the same. So the compass stores that information, and we can just check, yep, this is the same, right? I didn't adjust it at all. Okay, and so this is, likewise, the length of AC is the same as the length of AB. Okay. Now, AC and BC both have length AB, so they're also equal to each other, right? Note the length of AB is equal to the length of AC, which is equal to the length of BC. And so this triangle is equilateral. Right, so I didn't state it before we started down this path, but our definition of equilateral triangle is a triangle whose side lengths are all equal to one another. Okay, now you might have some objections here because you might say, well, it's not really clear exactly what assumptions we're making here. I don't think any of you are going to fight me saying that these three things are equal. Okay, but if we're doing this axiomatically, we kind of have to make some statements here, right? We have to say, okay, well, like I don't have much of a problem saying that these two things are equal, but then saying that BC and AC are equal because they're equal to the same thing, that's not. You're used to that. You're used to this property of the equal sign, but this is something that has to be stated. So in fact, Euclid states this as one of his assumptions in that, things that are equal to the same thing are equal to themselves. They're equal to, they're equal to each other, right? So, so this is an assumption that's made in the logic, okay? And so this construction shows the sorts of assumptions or axioms, postulates that we need to talk about if we're going to make it absolutely clear what we're allowed to do and when we're allowed to say we're done. So here we say that we're done. We have proven this. Okay. Going through this in words rather than just the diagram, I would say, okay, I start with my given length AB, drawing these two circles as I did in these two steps, guarantees what? Well, these other two line segments that I constructed, their length is the radius of circles centered at either A or B, but the radius is the same either way, and it's the same radius as the length of this line segment I started out with. Okay, and so all those lengths are equal, so this is an equilateral triangle. Okay. All right. So what is going on in this construction? So in this construction, we have one, construction axioms. I'm going to use the word axioms and postulates interchangeably. Okay, so we have construction axioms. So these guarantee the existence of construction lines and circles. Okay. What do our construction axioms lead to in this particular example? So note the existence of the two circles, or the fact that I can produce those two circles. So the existence of the two circles and the two added line segments. BC and CA. Okay. Secondly, we have geometric axioms. Okay. So these guarantee the existence of points required for later steps. These guarantee the existence of points required for later steps. Okay. So in this case, note the intersection of the two circles. So the point C. Okay, that we chose. And yeah, so as Jackson noted, yeah, it's the transitive property that you're fighting over here. Okay. Which is what comes into play here in the third bit, which is logic. Of course, the idea, you are using some principle of logic that is, that is something that you can assume in whatever system you're dealing with. So for us, this is the notion of equality and the fact that the equal sign has the transitive property. In this case, so this guarantees, so these guarantee that certain conclusions follow So note, in this case, we're saying that the length of BC equals AB, and the length of CA, or we'll say the length of AB is equal to the length of CA, implies that the length of BC is equal to CA. Okay, oh, I'm off screen. Okay. So the reason I listed these things out is basically to call your attention to the fact that these are different things. Right now, the only thing that we have discussed is a construction axiom. So we've listed these. Okay. We haven't exhaustively listed these yet. So haven't listed these yet. And we're not going to fully list them until the next chapter. This is the logic axioms. We're going to assume these are the obvious ones that are in use in any other branch of math that you talk about. But we're still going to discuss what we mean by the obvious ones here. The most important ones for us are these geometric axioms. So what is meant by those? So these were called Euclid's postulates. And like I said, we'll list them out later. So until we've listed these out fully, you might be slightly in the dark a little bit as to exactly what you're allowed to do. But the reason why this is a trickier thing to get into is that ultimately listing out these geometric axioms and really understanding the interplay between them, and especially understanding the most important one, which is the parallel postulate, is really the thing that allows you to see where Euclidean geometry becomes non-Euclidean geometry and where the study of other geometries come from. Right, so I mentioned this on Wednesday that there's more than one type of geometry. So Euclidean geometry is one type, and for all of human history until the 1800s, it was more or less thought to be the only type of geometry. But non-Euclidean geometry came about by trying to construct geometry that satisfied most of these geometric axioms that Euclid had put forth, but not all of them, namely not the parallel postulate. Okay, so it turns out that we can construct some geometries that satisfy some of these, but not all of them, and those lead to different looking things. They lead to different looking geometries. Okay, so one quick question is the following. So an equilateral triangle is an example of a regular polygon. It's the simplest example of one. So an equilateral triangle is an example of a regular polygon. Okay. So what's a regular polygon? So in a regular polygon, all of the side lengths are the same. All of the angle measurements are the same. Okay, this is a regular This is what a regular polygon means. Okay, so you already know that for an equilateral triangle, all of the angle measurements are 60 degrees, and you have three equal sides. The next thing that you might think of is the regular four-gon, right, or the regular six-gon. So these are examples of polygons you might think of next after equilateral triangle. And the question is, can you construct those things? Okay, so regular polygon, here's a quick definition. I said it in words, but I didn't write it out. So a geometric figure bounded by equal line segments meeting at equal angles. Okay. Okay. So, question. For which n is a regular n-gon constructible? When we say constructible, we mean constructible with compass and straight edge. Okay. Again, this, for us, this means using these tools only with those three rules that I listed at the beginning of today's lecture. So this is not a question of can you draw a regular 37-gon. Okay, that's not what's being asked here. It's whether you can construct one that is guaranteed to be a regular n-gon using only those tools, right? So no other things. And it turns out this is actually a hard question, right? So the answer is not technically, it's not totally solved. If you're looking for specific n, okay, what it turns out, so it turns out that it depends on another question. And the other question it depends on is for which m is 2 to the 2m plus 1 prime. Okay, now you might say, why is it related to this? I won't get into it fully, but it turns out that a question like this is actually more in the realm of number theory and algebra than it is geometry. So this does give us one thing. So for instance, what are the primes that result for this? So these are called Fermat primes, if they are prime. Okay, so these are called Fermat primes, and this gives us some funny polygons that are constructible using compass and straight edge. So one of them in particular is when m is equal to 2, this is 2 to the 2 squared, so it's 2 to the 4 plus 1, so it's 17. That's prime. This is going to lead to the construction of regular 17-gon. So we will construct regular 4 gons and 5 gons. So we will construct the square and a regular pentagon. When this is prime, when 2 to the 2m plus 1 is prime, then a 2 to the 2m plus 1 gon is constructible using compass and straight edge. So the simplest example of this is a 17 gon that was constructed by Gauss, I think, in 1796. So note 2 to the 2 to the 2 plus 1 is equal to 17, which is prime. And Gauss, when he was like 19 or something, Gauss constructed a regular 17 gon using compass and straight edge construction. This was in 1796, I think. Might have to revise that later. I'll look it up later, but I think it was 1796. I'll talk more about this a bit later, how this issue comes up. That is unknown. So it was asked in the chat, are there known to be infinitely many of them? Technically unknown, although the answer is thought to be no. Of constructible n-gons. So of constructible n-gons, yeah, of this form, the answer is thought to be no, because it's thought actually that these Fermat primes, they are there's not that many of them, basically. I think basically it's thought that there's the first 5 and then there's no more. But that hasn't been shown yet. So technically that is open. So yeah, so we're not going to fully answer for which n is this regular n-gon constructible, but it is a full answer to that question is related to this question, which falls outside of the scope of this course, and also this, like I said, this still isn't solved. So anyway, so that's that. Let's do some more constructions here. So I think we have time for at least one more. So more constructions. So let's bisect the line segment. All right, so I specify a line segment. Here's my points that determine my line segment. All right, so there it is. I want to bisect, meaning I want to cut it in half, right? So bisect is the same thing as cut into 2 pieces of equal length. All right. So how do I do this? Well, my trick is kind of the same idea as I used last time, which is I find this distance using my compass, and then I draw 2 circles, one centered at A, one centered at B, having that radius. So I want to do the same thing. Again, I can, I didn't go quite far enough. Oh no, my eraser sealed up. Well, it's okay. So there's my, nope, that's the wrong end. If you get your own compass, you will remember suddenly that, oh, it's been like, you know, it's been like a long time. It's been like 20 years since I used one of these. I actually used one on, they have them in the math building. You can get, oh my God, that you can get for the chalkboard, like for the blackboard. And those are much worse to use than these. Those are really, really bad to use. Anyway, okay, so I have traced out my circle with much effort here. And I note that, oh, well, I have these two intersection points. So before, in my construction of the equilateral triangle, I only used one of these points. Here I'm going to use both of them. So we'll call this C, call this one D. And the idea here is if I draw in the line segment connecting C and D, this is going to bisect this line. Okay. All right. So this doesn't. This is the cut in two. Now, the question is, let's think for a second what is going on here. So first of all, what's something you note? One, if I've done this absolutely correct, looks like I might be a little bit off here, but if I've done this absolutely correctly, this not only constructs bisection of a given line segment AB, it also constructs a perpendicular. Okay, so notice that this is also perpendicular. So CD is perpendicular to AB. So this also yields a construction of a perpendicular line segment to a given line segment. Okay. Now, specifically, when it comes to construction of a perpendicular to a line segment, or to a given line segment, or to a given line, I could ask specifically for you to construct me a perpendicular to some given line or line segment that passes through a particular point. Okay, so I think I'll post this. I'll post this later today. That maybe your first homework will be to do exactly that, to construct a perpendicular through a point to a given segment. Okay, so looks like I've run out of time here. We'll continue on with these constructions on, well, I guess Monday is Labor Day, so I guess we won't do this again until Wednesday. So so next Wednesday we will continue on with the constructions, and that's going to lead us directly into this axiomatic treatment of geometry. So plenty more of this stuff to come. So anyway, I will see you all next week. Like I said, I'll post your first homework later today, and it'll be due, I don't know, sometime next week. So anyway, I will see you all next week.